5.6 is the fundamental theorem of algebra. We will use this theorem to solve polynomial equations with complex solutions. Yes, it has taken us until chapter 5 to get to the fundamental theorem of algebra that we've been talking about all year, but it's a really handy trick. Yesterday, we listed all the different possible roots with the rational roots theorem. The fundamental theorem of algebra will tell us how many solutions we should actually have. It states, if a polynomial function has a degree, n is greater than 1, just meaning the exponent value is larger than 1, then the total of number of roots, aka solutions, remember they're the same thing, is exactly the n roots. This includes multiple roots as well as complex roots like imaginary numbers. Now what is this all actually saying? It's saying if we look at the highest degree of our exponent, which we would use to classify this function, it is going to tell us how many solutions we will have. Since our exponent was a 6, we are going to have 6 roots, or 6 solutions. These could be real solutions, they could be fractional solutions, they could be imaginary solutions, but we will have a total of 6 in the very end. Let's say we want to find all of the roots of this given polynomial. Based on the fundamental theorem of algebra, since the highest exponent is 5, we know we are looking for 5 solutions. However, the way we find those 5 solutions has not changed from the lesson we did yesterday. Meaning the first thing we need to do is list all the possible rational roots. That means we're doing the factors of our constant term of 4 over the factors of our leading coefficient of 1, which would be 1, 2, and 4 over 1. Make sure we do plus or minus with each of these options. So we get plus or minus 1, plus or minus 2, plus or minus 4. Now, we need to figure out which one of these possible roots is actually a root. We'll start off with the easiest one, which is a positive 1. So we'd have 1 to the 5th minus 1 to the 4th minus 3 times 1 cubed plus 3 times 1 squared minus 4 times 1 plus 4. Does that equal 0? Thankfully, all of these values are actually opposites of each other, so 0 equals 0, and we know our first solution is that x equals 1. We have 1 solution down, 4 more to go. Since we know the solution, x equals 1 is a factor, we can do synthetic division. The 1 goes in our box. We are going to pull all the coefficients from our original expression, which would be 1, then negative 1, negative 3, positive 3, negative 4, and positive 4. Draw our division line, and we're ready. Bring down the 1, multiply to get 1. Add down the column to get 0. Multiply with what's in the box, that gives 0. Add down, get negative 3. Multiply by 1, it will stay as a negative 3. Add down, we'll get 0. Multiply, stay 0. Bring down, negative 4. Multiply, negative 4. Add, and 0. We now need to turn these coefficients into the actual quotient. Since we start off with an x to the 5th power, we are now starting off with an x to the 4th power. We have 0x cubed minus 3x squared. We have 0 x's and then negative 4 for the constant. So here is our quotient. Next, we can use that quotient and factor to find all of these solutions. So we have x to the 4th minus 3x squared minus 4. We have 3 terms, no greatest common factor. We can do that AC method. So what are those factors that multiply to a negative 4, but then add to a negative 3? We could do negative 4 and a positive 1. We're now going to replace this negative 3x squared with a negative 4x squared and a positive 1x squared. Remember, this was a negative 3x squared, which means we need to use x squareds to replace that middle term. Then we can fill in the x to the 4th and the negative 4 on the ends. Split it in half, pull out the greatest common factor, which is x squared, leaving you with x squared minus 4. Greatest common factor on the other side is a positive 1, so also x squared minus 4. And that leaves us with x squared plus 1 times x squared minus 4. Now we always check to see if we could go further. With the x squared minus 4, this is difference of squares, so this can become x plus 2 times x minus 2. and we can keep it x squared plus 1. Set each of these equal to 0, and x squared plus 1 equals 0, x plus 2 equals 0, x minus 2 equals 0. So that means x squared equals negative 1, take the square root of both sides, and x is going to be equal to plus or minus I, since that is what the square root of negative 1 is. In the next factor, we'll solve, so x equals negative 2, and add 2, x is also equal to positive 2. So here we get two solutions with the plus or minus I. We get another solution with x is negative 2, another solution, x is positive 2, and then from that second step when we were testing our roots, the fifth solution is x equals 1. We were looking for 5 solutions, and now we have found all 5 of them. Now that we know how the fundamental theorem of algebra works, we can use a shortcut with graphing. We're still going to first look to see how many solutions we should be having. Our highest degree is to the 4th power, which means we're going to have 4 solutions. But we can find the real solutions by simply graphing the function. We plug it into Desmos and touch on the x-axis, and we find 2 out of those 4 solutions, negative 3 and positive 3. We'll write those solutions out, and we know that x is equal to 3 and negative 3. Now we're going to do synthetic division with all of the roots. So if you have more than one real root, you need to do synthetic division more than once. It does not matter which one you start with. Let's just say we start off with the 3. We'll grab the coefficients again from the original polynomial, which is 1, 1, negative 7, negative 9, and negative 18. Bring down the 1, multiply to get 3, add for 4, multiply for 12, add for 5, multiply for 15, add for 6, multiply for positive 18, and we get that remainder of 0, which we should have because we already know that 3 is a solution. Now we're going to do synthetic division again. We're going to take the answer from our first round. So we have 1, 4, 5, and 6, and we're going to use that as the coefficients for the second round, where we're now using our other solution of negative 3. Make our division line, bring down the starting value, multiply to get negative 3, add for 1, multiply negative 3, add for 2, multiply negative 6, add for 0. So now that we've done all of our roots, we're ready to write out the polynomial that's left over. Normally we would decrease the exponent value by 1, but since we've done this 2 times, we're going to decrease it twice. So now we have an x squared plus x plus 2. That is our quotient that's left over. We can rewrite that here for step 3, x squared plus x plus 2. We're going to take this answer now, and we can either apply the quadratic formula, or we can factor. There's nothing that's going to multiply to a positive 2, but add to a positive 1, so we're going to use the quadratic formula in this case. So we have negative b, or negative 1, plus or minus the square root of b squared, minus 4 times a, which is 1, c, which is 2, all over 2 times a, which is 1. So that will give us negative 1 plus or minus the square root of 1 minus 8 over 2, which becomes negative 1 plus or minus the square root of negative 7 over 2. Take out that negative in the form of an I, so we have I square roots of 7. So we still have negative 1 plus or minus I square roots of 7 all over 2. So here are 2 of our answers. X is equal to plus or minus this imaginary value. But we also know from the very beginning that we have 2 real solutions. X is equal to 3 and x is equal to negative 3. So here are all 4 of the solutions to this polynomial. And we were looking for 4 solutions, so we found what we were aiming for.